Have you ever stopped to wonder how machines actually learn? I mean, really think about it. Today, we're going to pull back the curtain on one of the most important ideas in all of artificial intelligence. Let's dive right in.
Okay, think about this. You punch a destination into your map app, and it spits out an arrival time. And what's crazy is it's usually spot on. How does it do that? It's not just looking at the speed limit, right? There's something much, much smarter going on.
Well, here's the secret. The app, or rather the model behind it, has learned how to do this. And it learns by using an incredibly powerful process called gradient descent. Honestly, this is the engine that drives a huge amount of machine learning today. So what the heck is it? At its heart, gradient descent is basically a method for training. Its entire job is to keep tweaking a model's internal settings, we call them parameters, over and over and over again, until it gets as good as it possibly can at making predictions. But, what does good as possible actually mean to a computer? Well, this whole learning process is built around one single, super important goal: minimizing something called loss.
Look, for any model, whether it's predicting your ETA or trying to find cats in photos, the main goal is to be accurate as humanly or, I guess, machinely possible. And to do that, we need a way to measure just how inaccurate it is.
And that's exactly what loss is. It's just a number. Think of it like a penalty score. It tells us how far off the model's guess was from the real answer. A huge loss number means a huge mistake. A tiny loss number means it's getting really close. So this is the key takeaway, right? It's super simple. The lower that loss number, the better the model is. The entire game is to get that loss score as close to zero as we possibly can. Now, to really wrap your head around how a model finds that lowest possible loss, we're going to use what I think is a perfect analogy: the journey of a hiker. Okay, picture this. Our model is a hiker, standing somewhere on a massive, foggy mountain range. The hiker's only mission is to find the absolute lowest point in the valley. In this story, the hiker's altitude, that's our loss. So, the bottom of the valley, that's the point of lowest possible loss, the perfect version of our model. So this whole journey, this learning process, it really just breaks down into three main steps. First, you gotta make a guess. Second, you adjust and try again. And third, you have to know when to stop. Let's walk through it. All right, step one, make a guess. Imagine our hiker gets dropped onto a random spot on the mountain, blindfolded. That's kind of what our model does. It starts with its parameters set to 0. It knows absolutely nothing. So as you'd expect, its first prediction is awful, which means a really high initial loss. Our hiker is way, way up the mountain. Now for step 2, adjust and repeat. This is where the magic really kicks in. The model uses a bit of calculus to feel out the slope of the ground right where it's standing. Then it takes one small step in the steepest downward direction. That one little step adjusts its parameters and guarantees the loss goes down. It just does this again and again and again, with each step taking our hiker farther down the mountain. And that brings us to step 3, knowing when to stop. Our hiker keeps taking these smart little steps downhill, but eventually they're going to get to a point where every direction is uphill. They've found the bottom of the valley. For the model, this is called convergence. It stops when the loss barely changes anymore. It's found the best settings it can. Okay, so enough about foggy mountains and hikers. That's the theory. Let's bring this all the way back to our real-world problem, predicting your travel time. So let's go back to our map app. See, we're building a really simple version that predicts your travel time based on just one thing: how many stop signs are on your route. We've got the data. Now it's time to let gradient descent do its thing. So just like our hiker, the model starts out completely clueless. Its internal settings are zeroed out, and it makes its first totally random prediction. And yeah, it was bad. Like, really, really bad. Just how bad was it? The initial loss value was a massive 151. That's our hiker standing way up on some peak, not even close to the valley floor. But then, the model did its thing. It ran that first calculation, figured out the fastest way to get better, and took just a single calculated step in the right direction. And check this out, this is what's so cool. After just one step, the loss plummeted from 151 all the way down to 80.93. Wow. It's still not perfect, but it cut its mistake almost in half with just one single adjustment. And it just keeps doing that, getting smarter with every single step. So when you boil it all down, that's really what's going on. It's this beautiful, patient process of taking one small, smart step after another, always hunting for the best possible answer. And that's why it can solve problems that are just way too complicated to figure out all at once. You know, this whole idea of breaking down a massive, complex problem into these tiny, manageable steps, it's truly at the heart of how AI is solving some of the world's biggest challenges.
And that kind of leaves you wondering, doesn't it? If something as mind-bending as machine learning can really be boiled down to this simple iterative process, what other huge challenges in science or business or even in our own lives are just waiting for us to solve them one small step at a time?
Hey, if you found this fascinating and you want to go deeper on how these concepts are actually used to build real products, I seriously recommend you subscribe to the AI Product Management Playbook by Deepak Dio. It's a fantastic resource. Thanks so much for tuning in.